Okay, so hello everyone. I hope you can hear me well. So today I'm going to talk about a new idea that we think can really enhance atom-like interactions and that we like to call selective radiance. I guess the first slide should be why we care about having a strong atom-like interactions. And in principle, we care about this because atoms allow us to store and manipulate non-classical light. And this is because atoms are quantum nonlinear systems, and they can be used as building blocks of more complex structures. So for instance, if we care about building a quantum network, or devise some protocol for quantum state transfer, or design some quantum gates, all of these quantum technologies require strong atom-like interactions. And of course, there are always problems. And the first problem is that atoms and photons do not like to talk to each other in free space. And so imagine we have an atom in free space and we send a laser beam into it. And the probability of this photon and the atom to interact is given by the ratio between the absorption cross-section of the atom, that scales as the square of the photon wavelength, divided by the mode area of the laser beam. And due to the diffraction limit, this number is actually very small. And so, in the paradigm of Cavity QED, there is a solution to this problem. And the idea is to place an atom in between two mirrors. Now, this previously small probability is going to be multiplied by the number of bounces of the photons in our cavity. And the figure of merit that tells us how good is now this photon-atom coupling is the cooperativity. That is just the ratio between the good couplings and the bad couplings. The good coupling is the decay rate of the atom into the cavity mode, G, and the bad coupling is the decay of the cavity mode and the probability of the atom to emit the photon into free space, that we call gamma prime. So in another more maybe recently explored paradigm, that of waveguide QED, the idea is again similar. Now we place the atom close to a 1D photonic reservoir, and the figure of merit that tells us how strong is the interaction between the photon that propagates through the waveguide mode or the guided mode of whatever structure is here, and the atom is the optical depth. That is, again, a ratio between good couplings, the probability for the atom to spontaneously emit into the guided mode of the nanostructure, divided by the probability of emitting the photon into any other mode that is not the mode that we care about. Again, this is kind of free space, so gamma prime. And once you have built your cavity or your waveguide, there's nothing that you can do to improve these figures of merit except putting more atoms. And traditionally, what this means is that now our figures of merit are increased or are multiplied by the atom number. So this has been explored in many experiments. So some examples are here where some groups are interfacing atoms with optical nanofibers. The idea behind these experiments is to just placing many atoms to enhance the atomic decay rate into the guided modes. Here, close to this place, I guess, Michelle Lukin's group is working in interfacing atoms with a photonic crystal cavity, and in the group of Jeff Kimball, there is an ongoing effort in placing atoms close to photonic crystal waveguides. The idea behind this experiment is maybe not so much about placing many atoms, but to instead increase the decay rate of the atom into the guided mode that you care about. So in all of these experiments and many others, the main idea is to increase the good couplings. What I mean is we either increase the atom number or we just increase the decay rate at which the atom decays into the guided mode that we care about. But what about the spontaneous emission into free space? So this is considered to be atom number independent. You just hope that it's small and you have to deal with it. And this is not really true in experiments. There are probably thousands of papers where the optical depth or the cooperativity are the figures of merit for basically everything. And one of the ideas of our work, and I think maybe one of the challenges in many Cavity QED, is can we go beyond that? So if we place more atoms in whatever, what does that mean? It's just that we have now a very big atom with a huge dipole moment, or maybe we can do something else with these so many degrees of freedom. So in this regard, I'm going to show you one, instead of these 1,000 papers, I'm going to show you one that I particularly like by Alexei Gorshkov when he was a PhD student in the group of Michalukin, that is called Universal Approach to Optimal Photon Storage in Atomic Media. And they say that basically it doesn't matter how hard you work. Every protocol for a quantum memory yields identical maximum efficiencies, which only depend on the optical depth of the medium. So this means that the infidelity, that is the error that one makes when one stores a photon into an atomic ensemble or when we retrieve it, scales as the inverse of the optical depth, which means that if we place more atoms in our, let's say, waveguide, or close to our waveguide, we will do better. But of course, we still have to fight against a spontaneous emission rate gamma prime, because the error is directly proportional to this number. Okay, so again, the spontaneous emission into free space is going to limit how well our atoms can perform a quantum task. And I have already discussed the conventional remedies to fight against this error, that basically all of them rely in increasing the coupling of the atom into the desired mode versus the coupling into all other bad modes. But we think there's something else that one can do. And the idea behind that is that at some point this gamma prime model has to fail. Because basically when atoms are close to each other, photon emission is when there's going to be interference. It's a wave phenomenon. So it doesn't even make sense to talk about gamma prime. So there's going to be some collective interactions. And the idea is that one can use these interactions to actually kill off dissipation. Okay, so before I talk about selective radiance, let me show you two very related concepts. The first one is that of subradiance. We have already heard about this today. But the main idea is that if we have many atoms coupled to the same photonic mode, these atoms are going to decay faster than a single atom would. So this is because there is constructive interference in the field that they emit. So they are subradiant. A very related concept is that of subradiance. And I like to think of subradiance as some sort of collective emergent camouflage behavior. So you can think, well, there's an example in nature about this. It took me a long to find out. But if you have one of these monarch butterfly, when it's alone, you can clearly see it and identify it. Apparently they like to be together, and when this happens, they look like this. So they are kind of hidden from us. And it's just some sort of butterfly many-body effect. So for atoms, it's not as beautiful, maybe, but something similar can happen. So when atoms are far away from each other, they do not interact. They emit photons at a single atom in rate. But when they are close to each other, the photons can interfere. And in particular, this interference can be destructive, which means that the atoms can become subradiant, and they hide from free space. So this is good, because this is the idea of selective radiance is to combine the best of both worlds of subradiance and subradiance. And this is the number one take-home message of my talk, is that selective radiance can enhance atom-like interactions, because the atoms are going to be subradiant into the mode that we care about, and are going to be subradiant into the modes that we don't want, those free space modes. And this is precisely what you want if you want to design an enhanced atom-like interface. Okay, so with this, here is the outline of my talk. I'm going to first discuss the formalism in which we describe these atom interactions. Then I will show you the physics of subradiance, so just a chain, one-way chain of atoms in free space. Then I will discuss what happens when the atoms are interfaced with a nanofiber, so this is selective radiance. And I will discuss how selective radiance can improve a quantum memory. And finally, I will talk about some kind of new results, or maybe a bit on quantum anomaly physics here. Okay, so first, the beginning. It's like, how do we describe this? We have atoms in free space, atoms close to a fiber, and if we have atoms in a cavity, we know how to quantize the field modes. But what if they are close to the most horrible dielectric you can think of? Right? So there's a prescription for doing that, and I'm going to guide you through it. So first, just to understand this a bit better, let's forget about the fact that they are, well, in any medium, they are driven by an electromagnetic field. It's trivial to find the field generated by this ensemble in any point in space. So the field is just the broad field or the quantum field, the driving field, plus the scatter field. And the scatter field is just the sum of the scatter field by each of the dipoles, which is basically the dipole moment of a given dipole times some function that propagates the field from this point where the dipole is to the point where we want the field to be calculated. and this thing is a propagator of the electromagnetic field that is called the Green's function. So in a more formal way, it's just the solution for the wave equation for the electromagnetic field. Okay, so great, we have solved the problem. Now the problem again is that atoms are quantum. And then it becomes a little bit difficult to find a prescription on how to do this, and I'm not going to show you the details, but the important point, I think that, so that you can believe what I'm going to show you next, is that to realize that classical and quantum fields propagate identically. So when a photon propagates, it doesn't matter if it's a classical field or not, it has to follow the wave equation. So in the end, the propagator, it has to be the Green's function. There is no way around it. So what we do is we just put hats on stuff. So previously complex numbers now are promoted to operators, and we have a generalized input-output equation, where now the field is the field operator is the basically depends on what previously was the dipole moment. Now is substituted by the dipole matrix element of the atom, and this is an atomic coherence operator that just describes a given atom going from the excited to the ground state and therefore emitting a photon. And again, the propagation is given by the Green's function. Okay, so now what remains is to solve for the dynamics, because we already know how to write the field. And to do that, this is kind of easy now, because these kind of interactions are delta-dipole interactions. So the Hamiltonian, as Dan has said before, is d dot E. We know how to write E, so then we know what's the Hamiltonian. And the Hamiltonian looks like this, and it describes this kind of flip-flop interactions where atoms are exchanging photons. And basically here we have something that looks like atom J goes from the excited to the ground state, emits a photon that gets picked up by atom I that goes from the ground to the excited state. And this photon propagation is mediated by the Green's function. So very simple. A couple of, wow, okay, now. So a couple of words about this. The first thing is that this Hamiltonian is not Hermitian because it describes dissipative processes where basically a photon is emitted and travels to infinity and you never get this energy back. And the second thing is that this is a very general prescription because it's valid for atoms close or embedded in any kind of dielectric, linear, reciprocal medium. So it doesn't matter if it's a free space, a nanofiber, this table, if one can calculate the Green's function, the electromagnetic problem is solved. And the only approximation here is a Bohr-Markov approximation, which is basically valid for everything I'm going to tell you later. Okay, so now let's apply this to the case of a chain of atoms in free space. So, okay. So now, imagine we have a chain of atoms in free space, and the Hamiltonian now looks very similar to what was before, but now the Green's function is that of free space. That is, basically you can find it then in any electromagnetism book, and it's trivial. It looks like this. So I'm going to tell you about optical properties, which means I can look only at the single-excitation manifold and diagonalize this matrix. So I'm going to have n atoms. I'm going to build an n by n matrix. The basis is just where one atom is excited and all the others are in the ground state, in the first, the second, etc., etc. When I build this matrix and diagonalize it, the eigenstates of these Hamiltonians are going to be collective atomic modes. And this just represents different spatial configurations of the atomic dipoles. And the eigenstates are going to have eigenvalues associated to them, and these are going to have a real and imaginary part. This real part is going to be the frequency shift of the collective atomic mode, and the imaginary part is going to be a collective decay rate. So this is the results for these frequency shifts and decay rates, normalized to a single atom and spontaneous emission rate in free space as a function of the lattice constant, normalized to the wavelength of the atomic resonance. And these plots are made for 30 atoms. So if I have 30 atoms, I'm in a single excitation manifold, I have 30 eigenstates. So at any vertical line in these plots, I'm going to have 30 points corresponding to the 30 eigenstates. So, okay, let me guide you through this plot. Basically, this means that if the atoms are very far away from each other, they should not interact because the Green's function decays in free space. Therefore, the frequency shift should be 0, and this is what happens, it's 0. And the decay rate should be that of a single atom in free space, and this is again what happens. When you start packing your lattice and the atoms are closer together, they start interacting. And in particular, once you cross a critical distance, that is half of the free space wavelength, you find that you have very dark states, subradiant states. So one thing that we realize is that one can understand these subradiant states in a useful way, at least for us and what remains of my talk. And we understand subradiant states as guided modes of an atomic chain. Okay, so instead of considering a finite chain, let's consider first an infinite chain. In that case, I can diagonalize my Hamiltonian using block waves, and I can plot the dispersion relation of my eigenstates. So this is the frequency, and this is the wave vector along this along the chain axis. And what I find for the dispersion relation once I diagonalize the Hamiltonian is this green curve. So, and it's centered around the atomic resonance frequency. On top of that, I can also plot the light cone. That is just pairs of sets of frequencies and wave vectors that allow light to propagate in free space. So this means that this region of my eigenstates that is inside the light cone couples to free space radiation. This means that these modes are actually the subradiant modes. Also, I have other set of modes that lie beyond the light line. These modes have a wave vector that is too large for them to couple to free space radiation. And so then one can do the same prescription for the field, use block waves, and one finds a trivial, let's say, relation between the wave vectors. That means that if your wave vector is too long in this longitudinal direction, the transversal wave vector has to be imaginary for this relation to hold. This means that these subradiant states actually create guided modes that propagate along this direction, but they are evanescent in this direction. So just to double check, we can plot the imaginary part of the dispersion relation. This is just the decay rates of these modes, because I said my Hamiltonian is not Hermitian, so I have this other part. And indeed, the decay rate inside the light cone is higher than that of a single atom decay rate. But as soon as I cross the light line, it becomes zero. So these are exactly the subradiant states. In particular, for an infinite chain, these are really subradiant states. The decay is literally zero. For a finite chain, this is not true. And then, of course, we cannot build finite infinite chains. So the question is, what happens when your chain ends at some point? And so, okay, what happens is this. So this is this is a plot for the subradiant, the profile, spatial profile of a subradiant eigenstate. So I have prepared this eigenstate, and it looks like this. So basically, it's like the atoms are one up, then the next one down, up, down, up, down, up, down. And because it's a finite chain, it also it has a cavity profile on top, right? And then one can wonder, okay, so if I have this eigenstate, I manage magically to prepare my atoms in this eigenstate. How does the field at the emit looks like? And it looks like this. So this is for 50 atoms, and you can see that the field is emitted only at the tips. So this confirms again the idea of subradiant states as guided modes. And the next question, and final question for subradiance is, okay, how does the decay rate scale? So how dark are really these subradiant states? And it turns out that they are quite dark. So this is the decay rate as a function of the atom number. And we find that the decay rate scales as 1 over n cubed. So this means that 10 of 100 atoms is about 1 million times darker than a single atom in free space. Okay, so with this, let me proceed with the physics of selective radiance. One could wonder, why do we care about selective radiance if subradiance is so full? You could put an excitation there and it will live forever. But there is a catch, and the catch is the following. So if I send a laser to prepare these states in my chain, I can only access this area, right? Because my laser propagates through free space. So it's going to naturally couple to the subradiant states, and I cannot couple to the interesting states I care about. So I need some light or something that has a dispersion relation in this region. And what is that? Well, any dielectric that has a guided mode provides that. So for instance, if I have a nanofiber, the nanofiber has a guided mode, and just because of the name guided, this has to be beyond the light line. So there has to be a point where the dispersion relation of both the subradiant states and the guided mode process, and therefore you can exactly excite these interesting states that are going to be subradiant in the free space and superradiant into the fiber. So let me show you a bit of how we write down these kind of interactions. So now it's a bit more complicated than in the subradiant case. And in this case, the atoms are going to couple through the guided mode. So now the Hamiltonian that describes this is kind of trivial. It just depends on the single atom decay rate into the fiber mode. And here there is going to be a factor that accounts for the propagation of the field through the fiber. Then there is another part that is the coupling through the non-guided modes. This is more complicated. So in principle, one could think this is going to be just a free space range function, but this is not true because yes, the presence of the fiber is going to modify the modes of free space. Luckily for us, an infinite cylinder with a circular section is one of the few geometries that where the semi-analytical expression for the Green's function can be calculated. This is very painful, but one can do the calculation, and we found this Green's function. So then we're ready to do calculations. And then the calculation I wanted to show you is that of a quantum memory, because one could wonder, well, it's very cool physics, is it useful for anything? I hope to convince you that it really is. So again, just as a reminder, the infidelity in a quantum memory scales as 1 over n, 1 over the atom number, if we don't account these interactions through free space. So just as a reminder, this is how a quantum memory works. The idea is that we initialize all of our atoms in the ground state. A photon that propagates through the waveguide drives this ground to excited state transition. And then now we need 3-level atoms. We need a metastable state where we can store this photon. And with an external laser, we're going to shine the laser into the atoms, and we're going to drive the population from the excited to the S states. Then we switch it off, and then eventually our photon has been stored in a superposition of S states that are metastable. So in principle, we could wait for as long as we wanted. In principle, I think, I don't know, maybe milliseconds, microseconds, I'm not sure, but maybe not so long. Eventually, we want to retrieve this photon, so we just do the time reversal process of this. We switch on the control field, and eventually our photon is going to leak out through the waveguide. But of course, there's certain probability that the photon leaks out to free space, and this is where the error comes from. And this is the thing that we want to suppress. Okay, so I wanted to show you a plot where we did this calculation. So this is a plot where I'm showing you the population in these S states. We're going to store a spin wave there. And I'm going to shine the laser externally. And as soon as I do that, you're going to see that some population starts appearing in the excited state. And this is for a chain of 200 atoms. And this is a plot for the loss as a function of time. And it's normalized the time so that at time 0 the photon is stored, time whatever, photon is released. And this is for a spatially uniform control. Okay, so this is what happens. Let's see. Yeah. So here is our polariton spin wave starts moving. The excited state population also starts moving. But suddenly there are points where as the spin wave moves, there is like a lot of sharpness in the edge of our chain. And sharpness is really bad because when you do the Fourier transform of a very sharp profile, this is going to have wave vectors all over the place. And some of the wave vectors are going to fall inside the light cone. And this is going to lead to loss. So we're going to do terrible. And indeed we do terrible. Just to double check, we calculated the loss, let's say properly, looking at the Hamiltonian and looking at the field emission, but we also calculated it by doing this Fourier transform at any time in the evolution of our spin wave in the excited state, and this is this gray line. So the idea that these wave vectors lead to loss seems to be true. So then we did, so then the crucial thing that we realized is that what we need to do is to minimize the wave vector components of our spin wave inside the light cone at all times in the dynamics. And how do you do that? So the one possibility is to basically use a non-uniform control field. And so it's a control field that increases in the edges. And the idea behind that is that, for instance, if you want to store a photon, as the photon propagates, it's not going to see a very sharp change in the refractive index here, but still instead something very smooth. So by increasing the control field at the edges of the chain, we're going to somehow taper the refractive index. And hopefully, this is going to lead to smooth profiles, which is what we require. So we did the calculation again. So now with this kind of crazy control field, but this is not a proposal for an experiment right now, so we can do whatever we want, I guess. And so let's make dynamical evolution again. And you see that this wave is really smooth, and it's going to be smooth for all the dynamics. And the loss is kind of 1,000 times smaller. So the idea works. And so the last plot that I'm going to show you regarding this selective radiance is a plot that we made for this loss or the infidelity as a function of the atom number. And I'm going to compare it with the previous result. And so here it is. So this is the infidelity, and this is the atom number. And this is the result predicted by Alexei. That means the infidelity scales as 1/n. And so if we consider these interactions to free space, and we're a bit clever, we managed to do an exponential improvement over this. So this is take-home message number 2 of my talk. Selective radiance can really improve the performance of quantum protocols. Okay, so just now I wanted to show you something new, something old, but something related to the topic of today. And the first thing I wanted to show you is some new stuff. So with this slide, you might think that I've been lying to you all along. I said that you can only do selective radiance if you have a fiber. And this is not true, at least if you keep an open idea of what selective radiance is. So let me explain this. If you have a 2D array, this has been studied well. Epidap is here, maybe knows more about this than me. But the idea is that if you have a 2D atomic array, and you send light into this atomic array that propagates normally to the array, if the distance between the atoms is smaller than a wavelength, this light is going to be totally reflected. And this is just because all other diffraction orders are subradiant. I mean, there is a destructive interference. So then we thought, okay, maybe one can use this to as a quantum memory. And then the idea is, well, among all the modes of free space, I can define one or a set of them that I'm going to call the good modes, and that these are going to be my detection modes. And the light that goes into all the other modes that I'm not going to detect, this is going to be my error. Okay, so then we did a calculation considering a Gaussian detection mode to be a bit realistic, and this is what we found. So this is what one found. This is the infidelity as a function of the atom number. At least with the physics of, let's say, ensembles, you should expect again this to scale as 1/n. And then we found this scaling that is kind of creepy, but it's an improvement. But the most relevant thing is that for an array of 4x4 atoms, this quantum memory already performs better than an ensemble with an optical depth of 600. So if any of you has arrays, maybe this is something that interests you. Okay, and then the maybe last thing I want to talk about is that I think what I have presented is many-body physics. We need more than 1 atom, 2 atoms, maybe 3 atoms to realize all this. But maybe it's not quantum many-body physics, because I've been telling you about the single-excitation manifold. So a question is, what happens if you go beyond that? So what happens is pretty cool. And what happens is that these more subradiant excitations or like higher excitations exhibit fermionic correlations. So this is cool. And the idea is the following. Imagine that now you look at the 2 excitation manifold and you diagonalize the Hamiltonian in this manifold. How do the eigenstates look like spatially? And they look like this. This is the atom position of atom 1, atom 2, and you see here there is kind of a gap. And this means that this happens because atoms, I mean, you cannot put 2 excitations on a single atom, right? So this means that when one looks at the 2 excitation manifold, one of the subradiant excitations can only use half of the chain, and the other can only choose the other half of it. They cannot be together. They don't like each other. So from something very local, that is the fact that you cannot put 2 excitations on a single atom, you're going to have some kind of beautiful Pauli exclusion in space. And this is also manifested not only spatially, but also in the decay rates, because how the decay rates of this subradiant 2 excitation eigenstates scale as, instead of 1 over n cubed, as 1 over n halves cubed. So again, it's like each of them works separately, so they cannot use the whole length of the chain. And also one interesting thing that I haven't said, so this is a plot for a chain of atoms in free space, but this behavior seems to be universal. This 1 over n cubed behavior, or 1 over n half cubed behavior, or 1 over n divided by n behavior when we have m excitations. And it can also be found, for instance, in waveguides. So if you have superconducting qubits and you couple them to a transmission line, you can think in looking at this physics, and this is something that we're now working on. And so with this, I'm close to the end. Okay, and Dan said that we should propose challenges and opportunities, so I'm very obedient, and there is my slide about that. I'm actually very excited about this correlated dissipation. I think it's a new way of thinking about how atoms and photons interact. And it has a lot of promise, but it's also very difficult to realize. And so I think one thing that one has to discuss is what are the possible experimental platforms to observe this physics. Most of my talk has been about atoms, but one could think about superconducting qubits, not to see selective radiance, but to see subradiance to the transmission line. Another possibility is solid-state emitters, but this presents challenges because solid-state emitters are different from each other. There is no homogeneous broadening, and maybe this physics is hard to access. If you choose to have atoms, then you have to arrange them periodically at a distance that is not trivial, because it has to be sub-wavelength separation. So how do you do that? You can use tweezers. Maybe for the 2D arrays, you can use maybe quantum microscopes. And then I think Chen will show us some beautiful spatially patterned nanostructures that maybe could be used to trap atoms. I haven't really talked about all the beautiful stuff. I didn't talk about the problems. There are problems, some of them obvious. What is the role of disorder? What is the role of finite filling fraction? What happens if your atoms move? Then this is only in free space, but if you now are even crazier and decide to put this close to a nanofiber, well, you have to master that, and this is not trivial. Another thing that can be damaging is hyperfine structure, because as soon as you have 2 ground states, there is, let's say, one channel of decay that you might not be able to kill due to subradiance, because you cannot establish coherence. And now this hyperfine structure problem was before a challenge, and now we're starting to see it as an opportunity. So it's very preliminary, but it seems to be kind of cool physics hidden there, and maybe it's another degree of freedom that we can use to see interesting subradiance. And I think the opportunities are really varied, because it's an open quantum medieval system out of equilibrium. So one can start looking into which kind of physics one can explore with this system. There is also, I have showed you how we can improve a quantum memory, but we can start looking into what happens with gates, what happens with entanglement protocols. Can we improve the errors of that? Well, in principle, I guess yes, but it's not trivial. Then maybe we can encode new clocks. What's the impact of all this stuff for metrology? What if the atoms move? This is interesting. So these are open questions. I don't know the answers, but I think it's exciting. And with this, I'd like to acknowledge everyone involved with this work that has been done in superposition between ICFO and Caltech. So in ICFO, Derek has been a very good leader in this project. And then I have also collaborated with 2 of his postdocs, Mariana and Andreas. In Caltech, I work with Jeff Kimball. And for the 2D array project, the main person to talk to is Marco, and also Alexi and Triporto and JQI have been collaborators on this. And with this, thank you very much. And if you're interested in this, you can read this paper.
Yeah, thank you.
Thanks.
Question.
How important is the uniform spacing of the atoms?
I think it's important because, so it depends on what you want to do. If you would say, do you have subradiance? If you have a little bit of disorder, preliminary calculation seems that you do have that. But the question is, would you have an exponential improvement if you, in your quantum memory, if you have disorder? My answer would be no. So I haven't checked that. But I think that as soon as you have disorder, if it's significant, that's in some ways kind of changing the refractive index of your perfectly guiding nanofiber of atoms. So this is going to lead to a scattering into free space. So I don't think it's a killer, but we haven't really said like, well, this is a bound of disorder that we can go beyond.
Maybe related to that, can you comment on the scaling with filling fraction?
Again, that's another thing that we looked into. So so the calculations I did a while ago was for, again, if you have subradiant states, if you have no finite filling fraction, and you do, maybe if you have 70 or 60%, you still have subradiance. If you go up, like below 50%, you have like something that I don't think you can call subradiance, because probably the scaling is not 1 over n cubed, it's sometimes into something weird. Again, I haven't looked at what happens if in your encoding of the quantum memory. So if your filling fraction again is not good enough, it's going to be the same. You're going to start scattering. But if another way of thinking about this, like if now suddenly I have a single atom missing, it's going to completely destroy this physics. I would say no, because it's like when you place two nanofibers together, you still have coupling in the near field between them. So it's not like you lose all the photons.
So the 1 over n cubed is actually interesting because I've thought in the past that imagine that you wanted to use subradiant states to take an atom that has an okay optical transition, but it just decays too fast. But otherwise, you'd love to use that atom to make some kind of measurement. So you say, I'm going to go to the, like, say I have a j equals n over 2 maximally symmetric state. Now I'm going to go and say, I'm going to actually figure out how to park myself in j equals 1. And actually, I'm going to use that state to make my measurement. Well, it's a subradiant state. You think, okay, so I'm going to be better off by using that. But it turns out now your quantum projection noise has gone up as a result of working to the state of lower j. And it turns out to be a wash. Like, yes, you get to measure for longer, but on the other hand, your quantum projection noise has changed. And you have to include the fact that your averaging goes like 1 over the square root of the Ramsey time. So you do it all at the wash. But in this system, you've got 1 over n cubed. And it really seems to imply that you could use this bath of other atoms to fix up your atom in such a way that you really could improve a clock. Now the downside to that is I could go to a maximally subradiant state like j equals 0, and that's a singlet state, and that actually has no phase that I can evolve as a function of time because it doesn't, like it just doesn't rotate. So I think it really would be interesting to ask, could you like take any old atom and basically surround it with lots of other atoms and kind of fix it up and build like a collective atom that has exactly the properties you want? It seems really, really interesting, that 1 over n cubed scaling.
Yeah, and also, I mean, this 1 over n cubed scaling seems to be true in almost every one-dimensional system, but if you go to 2D, it can be 1 over n6. So you become better, and if you go to 3D, it's also different. And you can play tricks. So if you, I mean, a way of thinking about this, at least for me, is, well, you can do analogs of photonics with atoms. So if you now change the lattice constant of the atoms slightly so that you make a region where the lattice constant is different from these other regions, then you create a photonic cavity. And then it's not 1 over n cubed, it's 1 over, I mean, it goes exponential. So there's a lot to play with, and the clocks is clearly one of the applications, but we haven't looked into that yet.
I have more questions. Everybody seated for coffee. Let's take time.